We will continue with the chapter on printed wiring board technologies. So far we have seen the introduction to this chapter on the fabrication methodologies for printed wiring boards, and we have reached a stage where we are discussing the substrates, organic substrates, and we have used the term called copper clad laminates to describe the base substrate that will be used for manufacturing or fabricating printed wiring boards. We have seen that basically when we talk about copper clad laminates, there are essentially three components. If you can recollect, a copper clad laminate CCL in short will consist of three components. One is the copper, second is the organic resin, and third one is the filler component. We have used schematics in the last class to see what each of these denote. Now, we are going to discuss in simple terms the manufacture of a rigid laminate. We will discuss about flex substrates or flex copper clad laminates much later. Typically, when you talk about manufacturing rigid laminates, essentially you require an organic resin. Okay. So, here the resin would be an organic resin. We have also seen different types of organic resins. Let us say in this particular example, we are going to use epoxy. We are going to use epoxy resin. And typically when you talk about the laminate structure, you require a copper foil to bond with the epoxy resin. But when you formulate the organic resin, there will be solvents. Typically, you will have one solvent, but in some cases you may have two solvents. So, you need to understand what kind of materials are involved. So, you can have an epoxy resin, you can have a polyimide resin, it could be a Teflon, polytetrafluoroethylene, and esters. We have discussed and listed various materials in the last class. The next component that is required for the manufacture will be the glass cloth or the glass fiber. So, essentially this is the filler material that we are thinking about. Now, the glass cloth or the fiber is now coated with the resin material. So, these two are mixed. How does it happen? You will have a container of resin into which the glass woven structure will dip into the tank and then come out coated with the resin. Now, the solvents will be air dried, and sometimes you can also use force drying by allowing it to go through a conveyorized oven at fixed temperatures that will remove the solvent. Okay. In some cases, partially the solvent is removed, because we are now going to prepare what is known as the pre-preg material or the B stage resin. So, at this stage most of the solvents are removed by drying. Okay. Now, pre-preg at this stage is a very important material that is used for multi-layer boards in PCB manufacture. It will act as the inner layer dielectric. It can easily sandwich to two copper foils by lamination process. So, the next step will be to lay the copper foil onto the pre-preg sheet. So, the pre-preg thickness could be 200 microns or 300 microns, 400, 500 depending upon the requirement, and then the copper foil thickness again is dependent on the various requirements in the market. So, assume that you are going to use a 35 micron copper foil on both sides, then suitably you can take copper foil and bond with the pre-preg sheets that has just been defined as a pre-preg or a B stage resin. Now, this structure of the dielectric material with the copper foil on top and the bottom is now fed into the multilayer press. This picture shows a typical example of a small multilayer press, where you have two stainless steel plates, okay, and your build up of the dielectric material and the two copper foils in this case is now fed in between the two stainless steel plates, and then they are pressed together at suitable temperature and pressure. And the timing is also very important, and as I said previously, the heating has to be slow as well as the cooling has to be controlled. You can't ramp up the temperature quickly to the required final temperature and remove it out of the multilayer press, giving it a thermal shock. So, this will affect the physical properties of the copper clad laminate. Finally, it is cut to size depending upon the market requirement. What you see here is basically a multilayer press. It can be custom made. Various models are available in the market depending upon your requirement and the volume of production. So, in a PCB industry, again we are going to use this multilayer press for laminating different layers that we have designed. Okay. So, if you look at this picture, you will see on the right side there is the stainless steel plates here, and then in between these books, as we call it, each build up structure is known as a book of laminate material. This will go inside the in between the plates, and then they will be subjected to the appropriate pressure and temperatures. So, essentially the components are, there will be a pressure gauge. You can see on the right side there is a settings panel for the pressure and the temperature. You can program it for the required timing, so that you can reach the maximum temperature in the required slow heating and slow cooling. So, there will be oil based cooling typically, and then you can see there is a stainless steel plate at the top and at the bottom. This is very typical of a simple multilayer press, and for large volume PCB manufacturing, the sizes can be large to accommodate the number of books that you require. Now, let us look at the laminates qualification. IPC, that is the Institute for Interconnecting and Packaging of Electronic Circuits USA, is one of the leading institutions that define or give periodically qualification and test procedures for qualifying a copper clad laminate. This is very useful for the industry. Now, the Department of Defense military has also brought out MIL standards for laminates qualification. So, if a company A produces these laminates, they have to follow some of these standards like the IPC, the MIL standard, or the NEMA standard, that is National Engineering Manufacturers Association, or the Underwriters Laboratory. Either of these, or in some cases a combination of these qualification and test procedures have to be carried out and certified for it to be able to sold in the market. So, the IPC laminate specifications will pertain to, there are various specifications. Some of the things are listed here. For example, 108 A and B pertain to thin laminate structures. Okay. Then 109 A and B pertain to glass cloth laminates, that means the physical properties, the thicknesses, and the tests to be carried out to qualify when such a material is used. 115 A B for rigid laminates, 125 laminates for high frequency applications. So, epoxy, for example, cannot be used for all applications. If you want to use high frequency application laminates, then you may have to look for better structures, better material, for example, Teflon or polyimides. So, you will look for those kind of materials. Mill specifications, mill S 13949 is very common, and the NEMA standard pertaining to laminate is 1989. So, it is better to be aware of these qualifications, and then you need to, if you are doing research or building a product using laminates of various types, you have to be aware of some of the qualification procedures and the certifications. So, you need to buy certified laminates. NEMA grades are commonly known as FR1, FR2, 3, 4, 5 and 6. Now, we will see what FR1 is. FR1 is a phenolic heavy paper base. So, here you can easily identify that the resin is phenolic based, okay, and the filler is paper based. So, from these grades, FR2 for example is a phenolic low paper base. Phenolic is a resin, it indicates what resin is used, organic resin, and it contains a paper filler, but the quality and the thickness of the paper might vary from FR1. FR4 for example contains an epoxy resin, it contains a filler which is glass base, and more importantly it is flame retardant. That is why we use the term FR, flame or fire retardant. So, if the material has to be flame retardant or fire retardant, there are again qualification procedures for the material to be certified as when it can be FR based. Okay. So, when an equipment using a PCB of FR4 or FR5 qualifications are used, and if there is some kind of a over voltage or short circuitry in the equipment, then the PCB, because being organic, can catch fire, or because of the fumes that emanate when the temperatures exceed certain limits, it can cause or catch fire, but it should have the ability to retard the flame by itself. That means, it should have a self extinguishing property. So, the material combinations like a epoxy or glass base with the fire retardant material in that can be used for such applications. FR5 is again epoxy and glass base, FR6 is polyester and glass base, and you have what is known as CEM material, which is a composite epoxy material. That means, in all of these cases the organic resin is epoxy, okay, or it could be a combination of other resins, but it contains different types of fillers. You can see, for example, in CEM1 you have epoxy, but at the same time you have woven glass and paper as the composite filler material. CEM2 is polyester, woven glass and paper, CEM3 is epoxy, non-woven glass and paper, and so on. Then you have mill grades. So, in certain cases people follow mill grade or buy mill grade copper clad laminates. You have GB, which is polyfunctional epoxy woven glass. Then in polyimide category you have GI and QI. GI means polyimide with a woven glass structure, and QI is polyimide and woven quartz material. For Teflon you have GP and GY and so on. Now, the cost variations are always there. If you look at this big list of NEMA grades and mill grades, all of them are not economical. Some of them are expensive because it targets certain specifications and applications. For example, it could be high frequency application, it could be for space applications. So, very common consumer electronics typically use the most economical FR4. Now, let us come to some other important details for a rigid laminate structure. Typically, core laminate thickness is 0.8 mm, 1.6 mm or 3.2. The copper thickness in the core can be 8 micron, 18 micron or 35 microns. Okay. In the case of prepregs, there are again different grades. Example 7628, very common number in the PCB industry, is basically 0.19 mm thick and the weight is 200 grams per square meter. So, this has evolved over the years, these kind of numbering systems. For example, if you want to manufacture or use a 1.6 mm FR4 type laminate, FR4 is epoxy plus glass, 1.6 mm thick, then you can use 8 layers of such, because 8 into 200 micron thick, typically about 0.2 mm, will give you 1.6 mm thick FR4 laminate. Another one is 2125, which is 100 micron thick FR4, which contains 88 grams of the material per square meter. So, these are the kind of notations that are available. In this box, you can see various types of material listed. There are more, but we have listed here a few of them. 7628, 2116 for example is 0.115 mm thick, 2125 is 0.1 mm and for example 106 is 0.05 mm. So, depending upon the buildup of your multilayer structure, you can pick the various prepreg grades and accordingly build your multilayer board. So, I will give you an example. If you have a multilayer board to be made and if you want to make a 0.8 mm finished thickness of your multilayer board, then you can start with a specific core which can be 0.4 mm and then the layers can be built for the remaining 0.4 mm by choosing various thicknesses of prepregs and copper foils. So, prepreg plus copper foil thickness knowledge is very important for a manufacturer. Now, the question is, so how is FR4 substrate dielectric prepared? We have seen FR4. I want to re-emphasize that it is a glass fiber epoxy laminate, most commonly used PCB material. 0.8 mm FR4 grade uses 4 layers of glass fiber material. Now, is FR4 green in color? Because I have shown you various samples over the last few lectures. Is it green? No, the basic FR4 material is not green in color. The green color that you have seen in most of the samples is basically coming from the solder mask color, which is green, and solder mask is one of the final applications or final processes on the finished PCB. So, this FR4 material is usually transparent in color. Now, we look at some of the laminate properties. We look at physical, thermal, electrical and environmental requirements. Now, physical properties, laminate integrity. So, these are the properties that a manufacturer will check and pass it on to the consumer, end consumer. Laminate integrity, what does it mean? So, we are worried about the laminate thickness. If we say it is 1.6 mm, there will be a tolerance, but the dimensions have to be maintained. Resin starvation, we talked about resin plus the filler mixing together in the initial stages of the B stage resin manufacture. At that stage, the resin should completely wet the filler material. For example, the glass cloth in FR4 should be completely wet with the epoxy resin. So, at that stage there should be no voids or starvation of the resin material. It should fill all the openings in the glass cloth. There should be no foreign particle inclusion or dust or moisture and other foreign materials like hair or other impurities, because once it is embedded in the structure, it is going to be very difficult to remove that, and it is going to be carried away to the final PCB. The second point is bow and twist, very important as it induces strain on the solder joint. Now, the laminate should be very flat and there should be no warpage. So, the storage also becomes very important. How you store your laminate? It should be stored flat, okay, horizontally. It should not be kept standing. Now, the bow and twist property is important because it also indicates how the manufacturing has taken place in terms of the correct thickness of the dielectric and the copper on both sides, if it is a double sided board. Now, if there is a bend and if you have started fabricating the PCB, when the board experiences thermal shock during soldering and so on, there will be dimensional changes, there will be heat shock, thermal shock, and this will induce the strain at the solder joint because of this warpage. So, make sure that your PCB is flat. Flexural strength, another important property, ability not to flex under mechanical load, because we are talking about rigid laminates. Peel strength. Now, the copper, as I have drawn many times the structure, there is a dielectric and there is a copper here. Now, this point, the peel strength at this point is very important. We talk about delamination. The material should not delaminate from the base substrate. The base substrate is the dielectric. Now, this is the core. The core should not exhibit any delamination. How do you test that? In the manufacturing of the copper clad laminate, basically they take samples of this laminate and then allow it to float on molten solder. Okay. It gives a thermal shock and that it is allowed to cool, and then they look at the peel strength on those areas of the copper and try to see if the copper is peeling away from the resin material, resin plus filler material. So, this will give an indication of the peel strength of the electrodeposited or electroformed copper. They can also do burn-in test, and also during etching you can see if there is a delamination. Etching should take place only on the exposed areas of copper material to the etchant. The thermal properties that we are interested are the glass transition temperature, denoted by Tg. We have discussed this briefly in the last class. It is the temperature at which the polymer begins to soften, that is a glassy state, denoted by Tg. It is significant because the laminate will see a series of heat shocks during the process of the PCB, like soldering, hot air leveling of solder, burn-in test for reliability, and repair. Repair can be manual soldering. So, manual soldering can in fact give more thermal shock compared to machine soldering. Then we are interested in CTE, coefficient of thermal expansion. This property indicates the integrity of the material. Materials expand on application of heat. The composite material expands differently in different directions. So, you have CTE in the x, y and z axis. So, how is this important? Your PCB, for example, if it contains the epoxy glass as the core substrate, then the CTE in the x, y axis is around 15 to 18 and the z axis is around 45 to 60. Now, we are also talking about this material being used in conjunction with silicon. So, there can be huge CTE mismatch, and because of various thermal cycles, the board should have good dimensional rigidity, reliability. Okay. So, it should be stable, dimensionally stable. So, if the CTE, the coefficient thermal expansion is going to be very large, then it will affect your integrity of the board, especially in terms of registration, during assembly and so on. You can see various materials like epoxy glass, polyimide is only 5 to 18, epoxy aramid, which is a different type of a glass material, cloth material, it has got 6 to 8. So, it is better for a designer to know these characteristics. Thermal conductivity, generally all polymers are poor conductors of heat. Reinforcements are used to improve the thermal conductivity. We have seen how metal core is also used in the core structure of a PCB to remove heat, to act as a heat sink, because some packages like your processors can dissipate a lot of heat. So, it is better to remove the heat from the package to the body of the PCB using core metal structures, or other fillers can also be used. Flammability should extinguish within 50 seconds. I was talking this particular point when we talked about the classification FR4 and so on. So, certain tests are done to find out if it follows these flammability or the self extinguishing property for glass, epoxy. Other materials are also available. The other important property in a laminate is it should not absorb water. Moisture absorption should be less. Diffusion of water into the structure could create problems electrically. Okay. So, that is why we say the resin starvation should not be there, and the copper to dielectric bonding should take care of these kind of problems. Electrical properties, we are interested in understanding insulation resistance, both surface and volume resistance. Surface insulation resistance is basically the electrical resistance between two metal conductors on a substrate surface. So, if you look at a PCB like this, and if you have two parallel tracks, track 1, track 2, let us say, we are interested in the electrical resistance that this material, dielectric material, can provide. In addition, as you know, we are coating a solder mask material as a dielectric. So, these are all very important manufacturing steps that will take care of the integrity of your board in terms of electrical parasitics. Volume insulation resistance, here we are worried about the thickness of the dielectric material. Okay. Now, lower the thickness, again we are interested in the dielectric constant being very low, okay, and how copper on plane 1, copper on plane 1 and copper on plane 2 can function electrically in a much better fashion based on the thickness of the dielectric. So, the volume insulation resistance measured in ohm centimeters is also a parameter of importance for the designer. Dielectric constant or permittivity, all of you are aware of this basic concept of dielectric constant in a material. It is basically the electrostatic energy storage capability of the material, and it influences the signal delay in a system, or the signal travel speed, or you can call it as a propagation delay, signal propagation delay. If you talk about delay in a structure, a sandwich structure like copper and a dielectric, you can measure the dielectric, you can measure the signal propagation delay, and this in turn is related to the permittivity of the material. Lower the dielectric constant, lower will be the propagation delay. So, that is very clear. The other point is dielectric strength or breakdown voltage property. So, this structure, this sandwich structure can be subjected to a disruptive voltage in kilovolts measured between 2 points an inch apart. Okay. And then there are certain threshold values which we can utilize and check if it can qualify the current industry standards. So, these are the important things that we look for in a laminates. In addition, today I talked about the environmental aspects of laminates. Most laminates contain bromine as a fire retardant or a flame retardant material, but today bromine is banned. Bromine is um, a band material in the PCB or the electronics industry. So, laminates which contain bromine are slowly being phased out. Okay. So, environmentally, if you talk about the requirement for laminates, we are moving into an era where bromine is replaced by materials like phosphorus and so on. We are going to discuss about this when we come to lead free chapter, but it is better to understand the implications of the new legislations that come into the electronics industry. It has affected the laminates also. So, as a summary, we talk about substrates are organic, rigid, flexible, and they can be molded. The standards or the standardization bodies are JDEC for components, IPC for components assembly and manufacturing, NEMA for manufacturing, and military also covers components, manufacturing and solders. Then do not use substandard laminates. Electrically they are going to affect the board quality, thermomechanically also they will affect the board reliability. Substrate selection, as a designer, spend a lot of time in understanding what a substrate is, because it influences the performance of the board, especially in high frequency applications, high performance applications and strategic applications. So, designer, once again if I can remind you, freezes the laminate type. It is not the manufacturer who is going to take the FR4 or a polyimide or a Teflon. It is you, the designer, who has to decide what laminate you want for your electrical application or electronics application. So, now we will come to the board fabrication process step by step. Before that, you should know the safety procedures before entering the lab or your work spot. Okay. So, safety procedures are almost the same, but depending upon the concentration of certain processes in the lab, the safety procedures need to be less or more. So, understand the safety procedures before entering the lab. You need to know about the material safety, and you have the right to know about material safety. So, any workplace will have to give you material safety instructions. You can demand for it. Read the material safety data sheet that is available for every material. If you buy a chemical, along with it comes a material safety data sheet. You have to read them carefully to understand what are the implications of that chemical in terms of usage, health hazard, and in terms of the nature of the chemical, whether it is a poisonous chemical or if it is a carcinogenic material which needs to be carefully looked into in terms of handling and so on. Follow clean room work procedures. Clean room work procedures will again vary depending upon the classification of the clean room. We talked about clean room classifications when we talked about semiconductor manufacturing. It could be a class 10 clean room, class 100, class 1000, 10,000 and so on. Depending upon the clean room levels that you are going to work, you need to use proper governing methodology, proper clean room equipment needs to be in place. Make sure firefighting equipment is in place, make sure the nearest health center, security, telephone numbers are made available to all personnel working in the lab or in the work spot. So, this is a very general guideline I would like to give for all students and personnel working in R&D and other institutions. Now, we will have a look at typically what it means to have a clean room work procedure or governing procedure. So, have a look at this video, and I will also try to explain to you some of the highlights depicted in this video. So, essentially your clean room can be, as I said, class 10, 100, 1000, 10,000 and so on. This is the ESP lab in CEDT. What basically we are trying to show here is the gowning that you need to undergo. So, you need an apron, make sure the gloves are used when you are handling the boards, the chemicals. There are different materials that are being used in the PCB manufacture, for example, in our lab, and there are different sections of clean room in the lab. Nevertheless, gloves have to be worn. You have to wear a face mask that can protect you from fumes, acid fumes, alkali fumes or other organic solvents and so on. You need to wear a head mask that will prevent hair falling into the lab. As you know, hair thickness is very small, but a hair falling on a photoresist, for example, will be translated onto the PCB. Use goggles, very important for safety. Normally, in a lab or a manufacturing setup, there will be an air curtain and also an air shower. Any personnel entering into the lab need to have an air shower. The air shower is used because it will blow away all the dust from you, from your hair, from your clothing and so on, and this will prevent all this dust entering into the lab, because as I said, a dust or a peck of dust falling on a material in the surface of the PCB or on the surface of the PCB is going to get translated along with the design. Okay. This is the yellow room that you can see, and materials sometimes are very sensitive. Temperature and humidity conditions need to be maintained. For maintaining the clean room, here you can see HEPA filters are used. Basically, these are filters that are used to filter the dust. Okay. This is basically used to filter the dust, and then these are removed by an exhaust. So, you have a laminar flow structure, and this HEPA filters can basically remove all the dust from your body and from the clothing. So, this video has demonstrated typically how you have to enter the lab, because some of the yellow room activities, we say yellow room because some of the materials cannot be exposed to white light. So, we talk about now board preparation or surface preparation as the first activity in the board fabrication sequence. In the inset, you are seeing a printed circuit board. The color of the laminate here, as you see here, is almost transparent. So, the green color that we have been normally used to seeing as a finished PCB is basically the color of the solder mask material. So, we will now see how a copper clad laminate, which is the starting material, needs to be readied for transfer of image from your mask that you have manufactured pertaining to your design onto the surface of copper. If you look at a copper clad laminate, on the surface you will see a lot of organic grease. If you touch the copper clad laminate, your thumb impression or finger impression is going to be attached, because your hand is greasy because of the natural sweat, and along with it there is dust, and it is going to be transferred onto your copper clad laminate. Because of large storage, there can be accumulated particles and other dust material. There can be stains, because as you know, copper is very reactive or moderately reactive to atmosphere. Copper can react with the oxygen in air to form copper oxide. So, oil, debris from the equipment, greases from your hand or other chemicals, oxides, some other stains due to chemicals falling on the surface of copper, if unattended to. Generally, laminates need to be protected until it is used, but if not, nevertheless you have to treat the surface of copper. Now, the treatment is required because we are going to promote the adhesion on the surface of copper. How do we do that? As you know, you are now going to transfer an image onto the copper surface using a photoresist material. So, this photoresist has to adhere nicely onto the copper surface. First, you use organic solvents like trichloroethylene or isopropyl alcohol. Trichloroethylene is almost banned nowadays from being used. So, I would rather suggest use isopropyl alcohol. IPA stands for isopropyl alcohol, very safe chemical. You can even dilute it with water, it is miscible with water, and therefore, you can use this IPA for cleaning the surface of your copper. Now, if you use organic solvents, all the grease is removed. You can use hand cleaning or you can use machine based cleaning. Now, you can also do acid cleaning using mild HCl, hydrochloric acid, alkali cleaning using mild caustic solution. Okay. Caustic solution is basically hydroxide based solution. Then you have mechanical brushing using rolling brushes with aluminum oxide Al2O3 aluminum oxide impregnated into the fiber structure of brushes. Now, this will act as a very good mechanical aid to remove oxides from the surface, dust material from the surface. Another option is to use micro etchant. Micro etchant basically means removing very small thicknesses of copper from the surface, and typically we use ammonium persulfate. Washing then with deionized water. DI water is known as deionized water. There are no ions except hydrogen and oxygen in this water. No salts are present. So, tap water contains a lot of solvents. So, you have to treat it to get DI water, and finally, drying in controlled conditions. So, these are the number of steps that you can probably do for keeping a copper clad laminate surface clean. So, you can use both chemical cleaning as well as mechanical cleaning. The need for making the copper clad surface rough. When you get the copper clad laminate from the manufacturer, generally the surface is very smooth. If you use it as it is, your adhesive in the photoresist is not going to stick onto the surface. So, for aiding very good adhesion onto the surface, you have to remove a few microns of copper. So, copper is removed say let us say about 1 to 2 microns from the surface, and it also provides a larger surface area compared to the structure that you get from the manufacturer. So, all of these or a few of these or a couple of these, let us say you can use micro etching first, or first you can do an organic cleaning, then you can do a micro etching, then you can do a mechanical brushing, and finally, a quick acid rinse neutralizing with an alkali lens, and then washing with the DI water and drying in controlled conditions. During drying, you have to make sure that the water is totally removed, because drops of water again can affect the next manufacturing step. So, surface preparation is an important activity. So, we will now see a small video on the procedures which I have just described. Here you can see the copper clad laminate. There are drilled holes. This is now being acid rinsed, and mechanically using a fiber with impregnated alumina, you are scrubbing. Alternatively, you can use machine brushing, where you have rollers of the same type of fibers. The laminate is fed in between the rollers. You have water being sprayed from the top and the bottom. Sometimes you can use a jet slurry containing pumice. Okay. You can use water mixed with the pumice material, and then you can form a slurry, and this slurry can be sprayed from the top and bottom of the brushing machine. Then you have the abrasive rollers. Together it forms a very nice methodology for scrubbing and removing your copper clad laminate, providing a larger surface area, removing the oxides and so on. Now, during this process the organic greases can be removed, various other contaminants can also be removed. So, once again have a look at this video, because even for double sided board manufacture the holes are first drilled and the holes will create burrs. Okay. Burr is an important defect that you cannot ignore. So, these kind of treatment methodologies like the scrubbing can remove burrs from a drilled hole. The reliability of the board gets built right from this process step. So, board surface preparation can never be ignored. Finally, the board is kept in an oven, let us say 80 degrees centigrade, for about 10 to 20 minutes to make sure all the moisture is removed. You can also increase the temperature to 90 or 100, but it is sufficient to have at around 80 to 90 to remove all the moisture in about 10 minutes. So, these are all automated typically in an industry. What you are seeing is a typical prototyping activity. Now, the next step after the board has been prepared is the imaging process. What do we do here? We apply the photoresist. It can be dry or wet film depending on the design requirement. Photoresist is a light sensitive material. It has got short storage life, typically about 6 months only. So, if you buy a photoresist material, you have to consume this material in the process within 6 months, and you need to store it carefully in controlled light conditions like a yellow room. Most photoresist material are light sensitive. You cannot work in white light. Typically, they are polymers. They are manufactured by cross linking of polymeric material. They require an initiator. In this case, UV light is the initiator that we are going to use in this photolithography process. So, imaging here is basically a photolithography process used in semiconductor industry. The same thing we are using in the PCB industry. The only difference is the materials are different in both the cases. We are talking about different feature sizes in semiconductor and larger feature sizes in the board level activity. The wet film can be applied by dip coating, a process known as dip coating, spin coating, curtain coating or meniscus coating. Now, for large volume, some of these methods like spin coating or dip coating are not profitable or viable. For large volume, you have to go in for a method like a curtain coating or use a dry film methodology, which uses a vacuum laminator technology to coat the photoresist material onto the surface of the board. Now, all of these, whether it is a wet film or a dry film, they contain an adhesive material, and this requires to adhere nicely to the surface of the board. That is why the importance of surface preparation. There are advantages of using a dry film over a wet film, which I will cover at the end of this section on imaging, because firstly you need to know what is a dry film, what does it look like, and what is a wet film, what are the thicknesses you can get with a wet film or a dry film, and so on. And when do you use a dry film, when do you use a wet film? There are many companies today, some of the leading names are DuPont, Ciba, among many others, which manufacture photoresist material in very large quantities to the semiconductor industry as well as to the PCB industry. Some of the common organic names are polymethyl methacrylate, polyvinyl based, diazoquinones and so on. SU8 is a very recent innovative material, new material which is epoxy based, used for high density interconnect sequential build up structures, where you can use very thin material for creating vias on structures. Novolac resins are also used. Solvent, typically in earlier days people were using organic solvents, but today most of the process is aqueous based, because there is no health hazard. You can prepare the developing process. Okay, one of the important processes in imaging is developing. So, you can prepare an aqueous developer right in your lab. Have a look at this pictures. You can see these are some images of tracks that have been generated using a photoresist material. Now, on the left you see here in this particular picture a very nice image of a track which is 27 microns, and then the gap between two tracks is about 23 microns. So, this is very fine line imaging. Okay. This is a zoomed up image of a photoresist imaging process completed with a series of tracks, copper tracks need to be defined on the board, and you can see that the gap is 23 micron and the track is around 28 micron. So, this kind of resolution is required or expected from the photoresist material. Not all materials will afford this. So, you have to be very careful in choosing the thickness of the photoresist to achieve such very fine lines. We are talking about 1 mil line or 2 mil lines and spacing. Okay. So, if the surface of the board has not been prepared properly, this is the result. Okay. You can see that after the developing process of the wet or the dry film photoresist, you can see parts of it are held firmly on the surface, part of it is not held on the surface. This is a very good example to show defects during photoresist imaging process. And here again below we are seeing very fine line structures being done. For example, here this is a 40 micron track and the gap is around 38 microns. So, very fine lines sometimes are required in the PCB industry. So, what is a photoresist? A photoresist is an organic polymer which changes its chemical structure when exposed to UV light. So, our first job is to coat a photoresist and expose it to UV light using a mask. You remember the mask that we have prepared for the various layers. So, we use a mask and expose it to UV light. So, certain areas will be exposed to UV light and certain areas will not be, depending on the mask. So, it contains a light sensitive substance whose properties allow image transfer onto a PCB. There are two types of photoresist, positive and negative. A positive resist is one in which the portion of the photoresist that is exposed to light through the mask becomes soluble in the developer. Remember that after photoresist application, the next step is to make the image visible and also stable on the surface. So, we use a developer. So, in a positive photoresist, once the exposure to UV light is complete, the exposed areas become soluble and the portion of the photoresist that is unexposed remain insoluble to the developer and they will remain on the surface of the board. So, understand what a positive resist is. In the case of negative photoresist, it is a resist in which after applying using a mask apply UV light, the areas that are exposed to UV light become insoluble to the developer. So, there is a different set of a chemical reaction that takes place compared to the first one, the positive photoresist. The unexposed portion in this case will be dissolved in the developer that you are using in the next process. Okay. So, using the right combination of a negative or a positive mask and a negative or a positive resist, you can play around with the kind of image that you require. In some cases, your positive resist may be very good for fine line circuitry, but for coarse lines you can use a negative photoresist. So, depending upon the sequence in your multilayer board fabrication, this technology can be used for any other printing process, not necessarily PCB. So, depending upon various structures, these are very important if you are going to build micro via structures and fine lines on boards. Okay. So, a negative photoresist and positive photoresist have different chemical properties, or when they are exposed to the UV light, and resulting in a different solubility in the developer. So, use this very judiciously. Now, the process sequence will look like this: photoresist application and patterning of the circuit. So, the first thing is you have the substrate taken, then assume it is copper clad now. Now, you coat it with a photoresist material on the copper surface. So, this is the photoresist, PR stands for photoresist. Now, you use a mask. This is a mask, and you can see this is exposed to UV light. Now, depending on the photoresist, whether it is a positive or a negative, let us assume it is a, in this case, a negative resist. You can see the pattern, the red one, this is the pattern that is protected. Here it depicts a pad, but you can have multiple pads, multiple tracks depicting a circuitry. This is just an example to show an area of a circuit or a pattern that is protected. The other areas now can be removed. The other areas can be removed after developing process. Now, this original copper, let us say, is now etched away and retaining only the small area of copper that you require as a pattern, as a circuit. So, this is a very simple schematic that you can look at carefully and understand how a photoresist works. So, we will now continue with the imaging of the photoresist. We will talk about different photoresist materials. We will also have video highlights on photoresist imaging, photolithography, developing and so on, which will be in the next class.